myself in the corner here. I have got myself in the corner here. I've got to redo a quick problem that, but as part of this, I think this is lesson number 9 or whatever. Is we're going to go through, and in fact, I'm going to get you. This is going to cover Friday and Monday's class. And I should probably stop doing this because I don't want to have to redo this every year because takes a lot of time and it's fun, but I've got other things I need to be doing too. But anyway, I don't know why I told you all that. You don't care. I mean, I wouldn't if I thought that was like, well, that's your choice, Doc. Well, you're the one that didn't want to have a boring lecture every time, but today was kind of that way. But anyway, what what I'm going to show you is this problem that I did on the previous video, and Sam, our intrepid SI, said, "Hey, I think your time is wrong," and I even kind of stammered and he was right when we were trying to solve this. 81 beats per minute. Okay, I had this 81 beats per 60 seconds. Okay, well, that's still beats per second. I want to know how many seconds there is between beats. Okay, so when we calculated this, we got 135 beats per second. That's still a frequency. That's what Sam said. He goes, "Isn't that a frequency?" Yes. And so your time, and it just makes sense. There's going to be the time, the period between beats is good. It's got it. I mean, it's like if there had been 120 beats per minute, I'd have said, "Oh yeah, it's a half a second." Is the time interval. So it's actually 60 over 81. Hey, this is divisible by 9, isn't it? I mean by 3, isn't it? We get 20 over 27. Yeah. That's 3 and this, can't get any much smaller than that, but that's what that is, 23 over 27. So I apologize. I apologize for that. The pacemaker problem. So the time is actually whatever that boils down to be. I've got this stupid Casio calculator. I don't know how to use it. 20 divided by 27 comes out to be, it works nice, but 0.741 seconds. There we go. That makes much more sense. So t is equal to 0.174 seconds. And I did that analysis right, that you're doing 36.8% of the Q of the charge. Of the charge is equal to Q times e to the minus t over RC, where RC is the time gradient, and we're trying to find C. All right, I was in the ballpark, but since this is smaller like this, I think my C is going to be 10 to the negative 6 and negative 7 instead of negative 7, and some of the other numbers are going to change. So I screw that problem up every year, every semester. I don't know why I continue to do it, or even use that problem. If something's being a bad bear to you, do something else. Do something else. All right. So anyway, let's take a look. Let's take a look at some more of these slides on magnetism, and I'll just talk you through them real quick. I know it's going to be kind of dull. This we'll try and oh yay! This is all set up nicely. All right, so here we go. Definition of a magnetic field. We didn't even get to that. We were just playing with how the forces worked. We were just playing with this right-hand rule number 1. And we're going to do a right-hand rule number 2. One of your classmates who is a medical tech and works with CAT scans, MRIs, and X-rays said the next rule, he talked about the thumb rule. And I was like, I don't know the thumb rule. We call the thumb rule right-hand rule number 2. But anyway, so here's the magnitude of the magnetic field as measured in Teslas for good old Nikolai Tesla, who, between Tesla, Maxwell, that's where all this physics comes from. I mean, Tesla was the father of electricity. He just happened to work for a jerk named Edison, Thomas Edison, who was a brilliant, brilliant inventor, but probably, if you want to hear all about it in kind of a comical way, you can watch The Drunk History of Edison and Tesla. But anyway, we measured in Teslas, and 1 Gauss is 10 to the negative 4 Teslas. I think one of your homework problems might even deal in Gausses, because a Tesla is huge. It's like a Coulomb. You know, we said a Coulomb is like, like a bolt of lightning is 12 coulombs. Well, MRI machines might be, I don't know, well, I have to ask Tyler, but it might be a 4 Teslas, some of them. Huge. Maybe between 4 and 7 Teslas. And normally we work into 10 to the negative 3 or 10 to the negative 4 Teslas for our regular everyday magnets. We talked about the right-hand rule. So let's look at this. So let's calculate, because I had some problems. So we want to find the magnitude and direction. If it's 30 degrees, we got B is equal to 0. All right, so let's do that. Because this is classic. So here's what we've got. We've got a magnetic field. Okay. Got a magnetic field going like this. Got a proton flying through this magnetic field with V is equal to 5.0 times 10 to the 5th. What did they say? 5th or 6th? 6th and 0.4 Teslas. All right. Times 10 to the 6th meters per second, and the Tesla is, or the magnetic field B is equal to 0.40 Teslas. All right, and it's making a 40-degree angle here. All right, so now, I don't know why I drew that so short. We want to find the force. What does the force equal? Well, the force is equal to Q V B, and I'm going to draw the perpendicular sign there. There's your formula. Force is equal to the charge times the velocity times the magnetic field, the perpendicular component of the magnetic field. The parallel component does nothing. So we need the perpendicular component. Here's the parallel. Here's Bx. That does nothing. By is where we get the stuff. All right? So this comes out to be F equals Q V B sine of 40. Okay? So that's the force. And this is a proton. Hold up. I'm going to get my handy dandy trusty calculator out here. So we'll do this problem, then we'll move on. Then we'll move on. And I promise we'll move much quicker than this. All right. So, and it's a proton. So Q is equal to 1.6 times 10 to the negative 19 coulombs. So we'll just put in those forces. F is equal to 1.6 times 10 to the negative 19 coulombs times 5.0 times 10 to the 6 meters per second times 0.4 Teslas times the sine of 40 degrees. That's what the force is. So 1.6 second e to the negative 19, 5 second e to the 6th times 0.4 times the sine of 40. That's 2.057 times 10 to the negative 13 newtons. Not too much of a force. All right. What if that's for the proton? What about the force on the electron? Same thing, except it would be negative 2.057 times 10 to the negative 13 newtons. And by the way, since we've got By going this way. Okay, so it's the perpendicular. It's the perpendicular component of that. So, and V going like this. What's the direction? Right hand rule. Finger in the direction of this, going this. It's coming up out of the page at us. That's the direction. It's coming at us. This one, be going into the page. Okay? All right. Because we could also take, well, we could take the 40-degree component of the vector. Oh, it's the B field. Oh, I see what I did wrong. I had the B field going. I drew the B field straight across when the velocity vector should be going straight across. I think that's what they meant in their same thing. All right, still works out. Cool. Oh, and then the last thing is, so what would be the acceleration of the proton? Well, the acceleration of the proton is F over the mass of the proton, which is, you get a pretty huge number here. But the acceleration of the electron, the magnitude of the acceleration, is the force over the mass of an electron, which is, this thing is going to be huge. All right? It's going to be huge because why? This is a really small compared to this, like 9,000 times smaller. All right.